finally, let's talk a little bit about so-called scaling relations, and this turns out to be a very interesting subject. What's shown here are two different projections in a parameter space of radius, density, and kinetic temperature of elliptical galaxies, dwarf spheroidals, and globular clusters, sort of like two pictures I've shown you before, but here it's in 3D space. And in some cases, there are excellent correlations, and that's the interesting thing to understand. Now, scaling laws are called that way because there are mostly of them, there are power laws. You take log of two quantities, they scale in a linear fashion. And they're built there by galaxy physics and galaxy formation. So trying to understand where they come from is teaching us something important. They're also different for ellipticals and spirals and dwarfs and so on, so that tells us that there really are kind of different families of galaxies. There isn't really a continuum. And interestingly enough, if you can correlate something that depends on distance, like luminosity or absolute radius, with something that does not correlate with distance, say rotational speed, then you can measure the distance-independent quantities and figure out how far something is. This is just like using HR diagram to measure distances to clusters, where luminosity is distance-dependent, but color or temperature is not. And so by measuring color of a star, you know from the calibrated diagram what its true luminosity is. You compare it with the apparent luminosity, you know the distance. So this is how we can do that for galaxies. Well, there are two important correlations. One is for spirals, one for ellipticals. For spirals, there is a correlation between luminosity and maximum circular speed. That's called Tully-Fisher relation, and goes that luminosity is roughly as a fourth power of circular velocity, because mostly flat rotation curve. It gets a little better as you get from bluer filters into the near infrared, and that's probably because you just don't get fluctuations from young stars or dust. And it's an amazing correlation. It's good to about 10% of intrinsic scatter and maybe even 0. Now, why is this interesting? Well, because the circular speed is a property of the dark halo. And luminosity is a product of a stellar evolution of the disk. And the fact that they're essentially perfectly correlated tells you that somehow history of star formation in the disk is governed in some way by the dark halo, even though dark matter by itself does not interact with regular stuff in any other way than gravity. And understanding this is going to be a very interesting thing. So we don't know why it's so good, but it is, because anything we can think of will just spoil that correlation. For elliptical galaxies, there is something similar called Faber-Jackson relation, but the really interesting one is a bivariate correlation, which means there's a bunch of properties like radii, luminosity, densities, velocity dispersions, what have you, and any two of them can be expressed, can predict the third one. So just like Tully-Fisher relation is like a correlation on XY plane of luminosity and velocity, this one is a plane embedded in three-dimensional space of, say, measure of size, like radius or mass, measure of temperature, like velocity dispersion, and measure of density. And that's why it's called fundamental plane, and it's usually expressed in this form, scaling of radius with velocity dispersion and surface brightness. The two pictures here show what happens if you rotate this parameter space. The one on the left is you're looking at nearly face on. There is no correlation whatsoever. And then you tilt your point of view and look at it edge on, you see there is a beautiful correlation. And so this is actually pretty amazing, that any number of important properties of ellipticals are united into just two numbers. And why just that? We don't know, again. Why is it so good? Now, there is no mystery why there are these correlations, and you can go from just virial theorem, equate potential and kinetic energy, say what you observe is not the same thing as mean mass, radius, and so on. Lump all this together, and you say that for a galaxy bound by Newtonian gravity, radius should scale as velocity squared, surface brightness to -1, and mass to light ratio to -1. And luminosity should scale as velocity to the fourth power. Hallelujah, we recovered Tully-Fisher. Surface brightness to -1 power and mass to ratio -2 power. Now, if any of those deviate from perfection, then you're going to create some scatter. Now, we know that in reality, mass to light ratios, surface brightness, they all differ systematically or randomly. And yet, somehow things compensate to make perfect relations. So for Tully-Fisher, we got the right slope, fourth power of velocity. For fundamental plane, we did not. And that's due to the systematic deviations of structure of ellipticals from being perfectly homologous, meaning ellipticals are not just scaled version of each other, bigger and smaller but same structure. No, there is a systematic change in the way they're arranged internally as a function of their mass, and that tilts the plane from virial theorem into what's observed. So if you have galaxies bound by gravity, that means virial theorem applies, and they're almost but not quite homologous version of each other, then you expect to recover something like this. But any process that we can think of just spoils up these correlations, would puff them up into pure randomness. And somehow that doesn't happen. So instead of that, the opposite happens. And just like HR diagram was this two-dimensional space of luminosity and temperature, in which stars were on one-dimensional sequences, the main sequence, the red giant branch, and what have you. For galaxies, there is one extra dimension. There are 3 dimensions, one of which measures size, radius, mass. Another one that measures density, and a third one that measures the kinetic energy, rotational speed or velocity dispersion. And in that space, they're not on lines, they're on sheets. And different galaxies in different position. And so no matter where they start from, they end on one of these correlations. And nowhere else. So there's preferred dynamical states. And so the hope is that we can use this in the same way that HR diagram was used to develop theories of stellar structure and evolution and test the models. Our numerical simulations of galaxy formation can reproduce these correlations, but again, nobody knows why that and not something else.